All right, everyone, thanks for coming. Today we have Lior, who is a professor at University of Toronto, working in the maths department on extremal and probabilistic combinatorics and its applications to theoretical computer science. Lior did his postdoctorate at ETH Zurich, and he did his PhD under Asaf Shapira at Tel Aviv. And Lior will tell us about regularity lemmas for hypergraphs.
Do I need it? Okay, perfect. Thanks a lot for the introduction, and it's a great pleasure to be here. And thanks for coming. So I'll be talking about some recent and ongoing work with Asaf Shapira and Yuval Vigderson about hypergraphs of bounded VC dimension. And let me start with regularity and with the regularity lemma. So the basic definition that we need is a regular pair. So first we define the density. So if we have a bipartite graph with parts x and y, so the density is just the fraction of pairs which are edges. And we say that this bipartite graph is regular if whenever we pick two sets, one in x and one in y, and they are kind of large, so they're at least epsilon fraction of their parents, then the densities are close. So the density between x prime and y prime is essentially the same as the density of x and y up to an epsilon. And the intuition for this that you should have is that regular pairs are random-like. So in a random graph, you have this, and this definition is meant to capture a certain property of randomness. Okay, now in a random graph, you expect to have a copy of any fixed thing you want. So for example, if you want to find, so the really fat lines are edges and the dashed lines are non-edges. If you want to find a copy of this in your random bipartite graph, you're guaranteed to have it. And in this sense, the intuition of regular as random-like is correct. So it's true that any fixed bipartite graph that you give me, if x and y is epsilon regular, and the density of x and y is not too close to 0 and to 1, well, it has to be, right? Because if it's 0, then you will not find any edges. If it's 1, you will not find any non-edges. But in assuming this necessary assumption, if the regularity is smaller, significantly smaller than this gamma, then you can find a copy of this bipartite graph as what I call bi-induced, which just means you have edges where you need edges and you have non-edges where you need non-edges. Okay, great. So now there is this result that's called Semeredi's regularity lemma, and it's very influential in external combinatorics. It has many applications. And it says that if you give me any graph whatsoever, I can partition it into parts. I can partition the vertices into some bounded number of parts such that most of the pairs of the parts are epsilon regular. So I cannot really guarantee all pairs, but up to epsilon t squared of the pairs, all others are epsilon regular. And you can also, we can assume that they have the same size. That's also true. And then the question is, how many parts am I going to get? So let me tell you a proof sketch of the regularity lemma, and the reason I'm telling you this, I will later contrast this with a proof of a variant of the regularity lemma that does better in terms of the dependence. So the proof goes roughly like this. So suppose we have a certain partition which is not epsilon regular, we're going to have some density increment. So we will show that in this case we can refine this partition and something improves, and this something cannot improve indefinitely, so at some point we have to stop with the regular partition. So we do the following. So let me maybe draw a bit. So if it's not regular, so we have these parts, V1, V2, V3, and so on. And the fact that it's not regular means that we have many pairs which are not regular. So maybe V1 and V3 is not regular. This means I can find a pretty big chunk here and pretty big chunk here. So this is, let's call it V1 prime and V3 prime. And the density between V1 prime and V3 prime it deviates a lot from the density between V1 and V3. And I can do it, so there are many pairs like this, so maybe I can also do it for V1 and V4. So then I have another set here, which is behaves badly with respect to some subset here, and maybe also V1 and V6. So there is another set here. So I do all of that, but in the end I need a partition, so I'm not happy with this situation. So what I do, I take the Venn diagram of this thing. Okay, so I look at all the regions I have here, and this is my new partition. And I do this everywhere. And you can show that something improves. So something is something that is called the mean square density. So I'll not go into what it is, but this increases, and this is bounded. So this increases significantly by something like epsilon to the 4 or to the 5. And it's always at most 1, so this process cannot last more than 1 over epsilon to the 5 steps. But now if we try to understand how many parts we get in the end, so you see that if you have t parts here, in this Venn diagram you have t sets, so the number of regions can be 2 to the t. So from t you jump to 2 to the t. And this means that this proof, what it gives you is that the number of parts in the end is something like 2 to the 2 to the 2 to the 2, and the number of exponents is how many times this process runs, so how many iterations. And this is called the tower function. So this is a tower of height 1 over epsilon to the 5th. Okay? And surprisingly, maybe Gowers, maybe 20 or 30 years ago, showed that this behavior is unavoidable. So there exists a graph such that if you want to find a regular partition of that graph, you have to take a partition of this size for some constant c. So c is maybe 0.1. Okay, questions so far? Okay, good. Okay, so now let me talk a bit about VC dimension. So VC dimension is a notion that's used a lot in computer science and in combinatorics, in discrete geometry. So let me define it in the context of graphs. So the VC dimension of a bipartite graph xy is the maximum number d, such that I can find vertices x1 up to xd and vertices yi, where I goes over all subsets of d, such that xi makes an edge with yi whenever I is an element of the set I. So what this means that I have the vertices x1 up to xd, and for any subset that I pick here, let's say I want this subset, there is a vertex which is adjacent to those vertices and not adjacent to the other ones. Okay? And in this case, we say that this set x1 up to xd is shattered by this vertices y. Okay. So observe that to say that, so what does it mean that xy has bounded VC dimension? Or let's say, what does it mean that the VC dimension is unbounded? It means that I can find this vertices x1 up to xd and these yi's for any constant d. That means that I can find a bi-induced copy of anything, because any graph, I can embed it into one of these, right? Because here I take my vertices and I can choose any subset of them and have a vertex that's adjacent exactly to this subset. So I can build any graph like this. Okay, so to say that a bipartite graph has bounded VC dimension is the same as saying that it avoids some fixed bi-induced subgraph. Okay, and from everything we saw so far, if this bipartite graph is regular, and then the density of it must be very close to 0 or 1, right? Because we saw that if the density is not close to 0 or 1, then we can embed anything in it. Okay, so the conclusion of all of this is that graphs of bounded VC dimension have a very nice property. You can find a vertex partition of them such that almost all of the pairs have density close to 0 or 1. So we said the proof of this already. So what you do, you just, okay, before that, so you take a epsilon regular partition using the regularity lemma, and then you just know that almost all of the pairs are regular and they must have density close to 0 or 1. Now that's nice, but the size of the partition is huge, right? So the question that you can ask yourself is, can we find such a partition with some more reasonable dependence on epsilon? It turns out that you can. So to do this, there is this result of Lovaas and Szegety, and also independently alone Fisher-Newman, that graphs of bounded VC dimension have this nice property that you can choose a bounded number of vertices in X. So T is only polynomial in 1 over epsilon. D is the VC dimension, such that any other vertex you take essentially behaves like one of these xi's. So in what sense? So there is some I such that this vertex X has almost the same neighborhood as xi, and almost the same means up to epsilon the size of y. So in other words, we can partition X into a bounded number of classes, and in each class, every 2 vertices have roughly the same neighborhood. So here's the picture. Okay, so the proof of this, so this is not difficult, so I'll not go into it, but essentially it follows from something called the Sauer-Shelach lemma plus sampling. So Sauer-Shelach lemma is maybe the most fundamental result about VC dimension, and you can combine it with a sampling argument to get this. Okay. So this is this result again, and I claim that given this result, we can, in fact, we can do the following. So we can partition X into T sets and Y into T sets, and T is only polynomial, such that almost all of the pairs have density which is either very small, so close to 0, or very close to 1. So how does it follow? Okay, and such a partition, we will call it epsilon homogeneous. Okay, so how does it follow? So what we'll do, we'll apply this theorem, we'll apply it in X to find this x1 up to xt, then we'll apply it in Y to find y1, yt, and then we'll just take this as the partition. So we will partition X like in the picture in the previous slide, right? So we'll partition X into, for each I, we'll take all of the vertices that behave like xi. And similarly, we will partition Y, like yi will be all vertices that behave like yi. And you can show, it's not difficult to show that this partition is homogeneous. Okay? Great, so we see that for graphs, for bounded VC dimension, we actually have very strong results. So we have this homogeneous partition, and the number of parts depends only polynomially on 1 over epsilon. And this is useful. So this is useful to prove Erdős-Heinel results, if you're familiar, or to prove property testing results. Okay. So let me talk a bit, okay, not a bit, let me switch to talking about VC dimension for hypergraphs. So now we're looking at 3 uniform hypergraphs, so every edge has size 3, and the question is what's the definition, what definition of VC dimension makes sense? So what we want a similar situation as before, but now instead of shattering a set of vertices, we want to shatter a set of edges, of pairs. So, right, so we want a set of pairs which is shattered by some vertices yi, and this means that if I look at the union of ei, of the ith pair, with yi, then this is an edge of the hypergraph if and only if I belongs to capital I. Okay, does it make sense? Okay. And now the question is, what do we want to assume about this set of pairs? So now this is not vertices, it's pairs, so they can have some structure. So we can ask what structure we want to have. And there are 3 versions that people studied. So the first version is when I don't make any assumption. So it can be arbitrary pairs, and I usually think of them as a matching. So disjoint pairs. And let me call this strong VC dimension. So this is not a standard term, but I couldn't find a term for this. So let me call it this. Another situation is if I require these edges to form a star. So this is called VC1 dimension. And a third situation that people look at is that if I require these edges to form a complete bipartite graph. Okay, and this is called VC2 dimension. And I'm going to talk about each of these. Okay, so first about this, the first option, where I don't make any assumption on how these pairs behave. So it turns out that in this case, this behaves similarly to the graph VC dimension. So it's very, very similar. If I have a 3-uniform hypergraph and this strong VC dimension is bounded, then there are partitions of the parts of x, y, and z. The number of parts is only polynomial in 1 over epsilon. And almost all of the triples xi, yj, zk have density close to 0 or 1. Right? So it's like exactly the same statement for hypergraphs, so nothing new. So maybe this is not the interesting case to look at. OK. So now what we can ask is, if we assume there is bounded VC1 dimension or VC2 dimension, what can we say about the structure of the hypergraph? OK. So let me start with the VC1 dimension. So let me remind you what it means. So the dimension is less than d if I can find no star like this and some vertices yi such that ei union yi is an edge if and only if I belongs to capital I. Right? So that this star is shattered by these vertices. And equivalently, this is the same as saying that every link graph has VC dimension less than d, and a link graph is just a graph, right? So a link graph of this vertex x consists of all pairs yz where xyz is an edge. So to say that there is no star like this is exactly the same as saying that the link of x has bounded VC dimension as a graph. So it's maybe a natural problem, right? So you have a hypergraph and you assume that all the links have bounded VC dimension. What can you say about this hypergraph? Questions so far? OK. So there is a result. So Chernikov and Tausner studied this problem. They, in fact, studied a much more general problem. Maybe I'll mention it in the end. But in particular, they proved the following. So if the VC1 dimension is bounded, then there is a partition. So essentially, there is a homogeneous vertex partition. OK, so it's the same story. You can partition x into t sets. You can partition y into t sets and z, such that almost all of the triples, xi, yj, zk, have density close to 0 or 1. And the question is, how does t depend on epsilon? And their proof, they used infinitary techniques. So this gives no bound whatsoever, no explicit bound on t as a function of epsilon. And later, Caroline Terry, she made quite some progress. So she showed that you can actually take t to be, well, somewhat modest, so only double exponential in 1 over epsilon. And she conjectured that this is best possible. So double exponential is the truth. So the first result I want to tell you is that this conjecture is not true. So in fact, you can do exponential. So you can find such a partition of exponential size. And Terry has an example that shows that exponential is best possible. So this is the answer for this problem. Now, here's a problem that I would very much like to see solved. So let me know if you have an idea. So I think that even though you can only find partitions of exponential size, you should still be able to find one part, so x prime in x, y prime in y, z prime in z, that have density close to 0 or 1. And those x prime, y prime, z prime actually are much larger. They are of size polynomial in epsilon times x. So you cannot partition into sets of this size, but you can find one. OK. Questions? No question. OK. OK, so this is the result. I'm just restating it. So if the VC dimension is bounded, then we have an epsilon homogeneous partition of exponential size. And the proof is actually not difficult, so let me try to tell you the proof. So let's recall two things. So saying that the VC dimension is bounded is less than d. The VC1 dimension is the same as saying that all the links have VC dimension less than d. That's the definition. And what this means is that if I take any vertex in x, then I can partition y So if I look at the link of x, that's a graph between y and z. And this graph has bounded VC dimension. So by what I told you a few slides ago, I can partition y into some small number of parts such that any two y and y prime from the same part, they behave the same in the link of x. But what it means that the neighborhood in z of xy versus the neighborhood of xy prime is almost the same thing. Okay, so this is the property that I'll use. So here's the proof. So consider any x in x and y in y. And now, by this property, we can choose, there are many choices of y prime in y, such that y prime are in the same part of this partition. So all I'm saying is that we have x and y, also z, and I take x and y, and x gives some partition of y, and I just choose any y prime which is in the same part with respect to this partition. But now I can play the same game on the other side. So now I will take this y prime, and I think it should say y prime here. Right, it should say y prime. Sorry about that. So now I'll take y prime also has a partition here, xi of y prime. And now I'll take any x prime that is in the same part as x. So the thing that I got is that xy, which I started with, behaves the same as xy prime. This, I mean that they have roughly the same neighborhood in z. And this xy prime behaves roughly the same as x prime y prime. So the conclusion is, so the point is that I start with this arbitrary pair. And for this pair, I have many choices. So I have a linear number of choices here, so the whole size of this part, times a linear number of choices here. Okay, so right. So what this means is that for any pair xy in x times y, there are many pairs, so delta n squared, where n is the size, sorry, I didn't say, so n is the size of x and y. There are delta n squared pairs x prime, y prime, such that they have roughly the same neighborhood as x and y. And delta is some polynomial function of epsilon. Okay. So now what I can do, I can sample some pairs in x and y uniformly at random, and you need something like 1 over delta of them, maybe times log of 1 over epsilon, but it doesn't matter. And what we expect is that if we do that, then every pair, we expect that almost every pair will be related to one of those E1 up to ER. And the reason that every pair is related to delta n squared, so if you sample 1 over delta, you expect to catch 1. Okay, and if you add this log 1 over epsilon, it will increase it will make the probability that you fail very small. Questions so far? So what all of this thing gives is that we have a partition of x times y into sets. So almost all of the edges between x, y, we can partition into sets E1 up to ER. R is small. And if I take any two pairs in EI, then they have roughly the same neighborhood in Z. So the way I achieve this, I just take EI to be all of those that are related to this little EI. Okay, and I know that I cover almost everything. So now what I'll do, so this gives me a partition of the pairs between x and y. All right, so the picture is that maybe color red is E1 and color green is is E2, and so on. So I color these edges with R colors. And each of these sets EI has its neighborhood inside Z, right? So there is the set of vertices that make an edge with the pairs in EI. Now, it's not really one set because it's a different set for each pair, but these sets are close to each other, so let me just fix one of them. So there is this set, and then there is a green set, and so on, right? Maybe blue is E3. So what I'll do now, I'll take the Venn diagram of these sets, and this will give me a partition of Z into 2 to the R parts. Okay? So now what I'll do, so this is essentially most of the proof. So what I'll do now, I'll repeat this whole game, but now instead of x times y, I will take x times z. This will give me a partition of y. And I'll take y times z. This will give me a partition of x. I should say x here. And so we have these partitions, and one can show that this gives an epsilon homogeneous partition. Okay, so I'll skip this part, but that's the proof. Okay, questions? Okay. Okay, so that's what I wanted to say for VC one dimension. So let me talk about VC two dimension. So this is kind of a new topic. If you haven't followed, you can start following again. So let's recall what does it mean that the VC two dimension is bounded. It means that is unbounded, sorry. It means that for every k, I can find a complete bipartite graph, k times k, such that those k-square edges are shattered. It means that for any subset of these edges, I can find a vertex that makes an edge exactly with these edges. So this is x1 up to xk and y1 up to yk. And now if I take any subset of these k-square edges, I can find the vertex that makes an edge exactly with those. And observe that I can construct any tripartite three uniform hypergraph in this way, right? Because I'll just take right? So because I can really insist on any subset of these pairs. So this definition of having bounded VC2 dimension, it's the same as saying that I avoid some three-partite, three-uniform hypergraph as an induced subgraph. So this is kind of maybe the nicest analog of the graph case. Okay. So now the natural question is, what if we assume that this is bounded, what can we say about the structure of the hypergraph? Okay. So now there's a standard example that shows you that hypergraphs behave not like you expect. So here's the example. So we will take a random graph between x and y, a random graph f between x and z, and a random graph g between y and z. Let's say with probability 1/2, but it doesn't really matter. And our hypergraph will be the set of all triangles in these random graphs. Okay? So I claim that this hypergraph has bounded VC2 dimension. So let me try to convince you of this. Let's consider the following tripartite hypergraph. So we have x1, x2, y1, y2, z1, z2. And x1, y1, z1 is not an edge, and everything else is an edge. So I claim that we cannot find this. Okay, so why can't we find this? Well, whenever I have an edge, it means that in the random graphs, so for example, if I have this edge, it means that those are all edges. And the fact that I have all hyperedges but this means that I must have every single edge that I can. So all 4 edges between x and y, or 4 edges between y and z, and all 4 edges between x and z. But then this edge cannot be missing. It will also be an edge. Okay? So in this example, I cannot find a copy of this. Okay. Okay, but on the other hand, this example does not have any homogeneous vertex partition. So if you want to partition your vertices into some bounded number of parts, and you want all the densities to be close to 0 or 1, this is impossible, because these random graphs have the property that, so if this is x, y, and z, if you restrict to any reasonably big subsets, then you will still have many triangles like this. Okay, so you'll still have many edges, and you will also have things which are not triangles, so you'll have many non-edges. So you cannot have density 0 or 1. So somehow vertex partitions are not the correct notion for VC2 dimension. Okay, and this is kind of again, this is a standard example that shows that hypergraphs behave differently. Okay. So bounded VC2 dimension doesn't guarantee that we have homogeneous vertex partitions. So can we get homogeneous something? So what would be the right thing to look at? Okay, so before I move to that, let me tell you a bit about how hypergraph regularity works, because it's very related. So we saw the definition of graph regularity, and the point was to kind of imitate a random graph, and we saw that it worked. So really, the definition guaranteed to contain any fixed subgraph, so in this sense, it does work like a random graph. So what would be the correct definition for hypergraphs? So here is the first attempt. So the natural way to go is to say, okay, when is the hypergraph XYZ regular? If whenever I take big subsets x prime in x, y prime in y, z prime in z, the density of x prime, y prime, z prime is roughly the same as that of x, y, z. Okay. Now the problem is that this doesn't guarantee that the hypergraph contains whatever you want, right? So the same example that we showed in the previous slide satisfies this definition, is very, very regular, but there are hypergraphs which it doesn't contain. So this is not the correct notion for hypergraph regularity, at least if we want to be able to embed anything. So the counting lemma doesn't work for this. Okay, so what is the correct definition? So let me tell you the correct definition. So it's a bit complicated, and so I'll be a bit vague in some places. What we do, let's consider a bipartite graph between x times y, and a bipartite graph between x times z, and a bipartite graph between y times z. So the picture is that so here we have some graph, we call it E. Here we have some graph F. And here we have some graph G. And what we're going to measure, so first we'll count how many triangles there are given by those 3 graphs. So how many ways can I choose 3 vertices such that this is green, and this is red, and this is blue. So this will denote the number of such triangles, and what we will measure is the density of H with respect to these triangles. So the density with respect to the triangles is how many of these triangles actually make edges of H. And regular will mean that if I pass to big subsets of E, F, and G, so E prime, F prime, and G prime, then this density, okay, big means that there are many triangles. In E prime, F prime, G prime, then the density of H with respect to these sets is roughly the same as the density with respect to everything. Okay, so it turns out that this is the correct notion of regularity that does allow you to count things. So somehow when you deal with 3 uniform hypergraphs, it's not enough to partition the vertices. Like regularity is not enough to do it with respect to the vertices, but you have to do it with respect to the pairs. Okay, and in order to make this useful, we have to be able to count how many, we have to be able to work with the triangles spanned by E, F, and G. And to do this, we actually assume that those graphs are very regular as graphs, because this allows us to count exactly how many triangles there are. This makes this whole thing possible. Okay. And then for this definition, the counting lemma is true. So if H is epsilon regular, and the density of H, meaning, where is it? This density with respect to the triangles is not too close to 0 or 1, then we can embed a tri-induced copy of every fixed tripartite hypergraph. So, right? So that's just the analog of the counting lemma we saw for graphs. Okay, questions? Okay. And then there is, so maybe 20 or 25 years ago, people proved for the first time a hypergraph regularity lemma, so they managed to find the way to generalize the graph statement. And the statement is that if I give you any 3 uniform hypergraph with parts x, y, z, then you can find this regular partition, which means you partition the vertices of x, y, and z, and then you also partition the pairs into, you partition them into the sets E, F, and G, such that if you, for most of the choices of E, F, and G, the hypergraph will be regular. Okay. Okay, now, what is the dependence that you get? Well, in the graph case, it was tower. Here it gets even worse. So the reason is that you have to prove this, you have to apply the graph regularity lemma iteratively. So you have to iterate this. So what you're doing, you're iterating this tower function. And this has the original name of Wowzer. So this is called the Wowzer function, which means, so Wowzer of x just means tower of tower of tower of tower x times. And so the bound for the 3 uniform regularity lemma is a Wowzer of height of poly 1 over epsilon. Okay? And interestingly, this is actually tight. So you cannot, so somehow what people understood in the last maybe 10 years or 5 years is that these proofs for regularity lemmas, they're often tight. So it was not easy to show that they're tight, but somehow this phenomenon comes up again and again, that you have this proof that gives this crazy function, but actually you need this function. Okay. So now let's go back to VC 2-dimension. So Chernikov and Tausner, and then also Terry, they proved the following. So here is what we can say about a hypergraph if the VC 2-dimension is bounded. So if it is bounded, then there are partitions, but now instead of partitioning the vertices, we partition the pairs. So it's not true that we can have a homogeneous partition of the vertices, but it is true that we can have a homogeneous partition of the pairs. So we partition the pairs, so x times y we partition into some E1 up to ET, and x times z to F1 up to FT, and so on. And such that for most of the choices of EI, FJ, and GK, the density of H with respect to these triangles of EI, FJ, GK is close to 0 or 1. Okay, so again, I essentially told you the proof of this already. So all you do is you apply the regularity lemma, and you observe that every regular piece, because the VC 2-dimension is bounded, so there is something forbidden that you cannot find, it means that the density is close to 0 or 1. Okay? And because we're using the hypergraph regularity lemma, we get a bound of Wowzer. Now, and Terry asked, can we improve this, or can we do anything better? So the second result that I want to mention is that we can do better. So it's still a very fast-growing function. It's a tower, but we can do better than the Wowzer. Okay. Questions? Okay. So this is just, I'm repeating the same thing. So this is a theorem, and we can take this T to be tower of height 1 over epsilon. And another question that I would very much want to see solved is, can you do much better? So can you take something of size polynomial on 1 over epsilon? Or if not polynomial, can you do it exponential or double exponential maybe? So anything which is not tower type. Because I don't know of any examples that are not polynomial. Okay. So the last thing I want to do, I want to tell you a little bit about how we prove this. So this is much more complicated than the previous proof, so I'll not really, so I'll only give you the rough idea of how this works. And for this, I need to talk about something that's called cylinder regularity. So the key tool that we use is something that's called the cylinder regularity lemma. So let me tell you what it means, and let me start with graphs. So graphs are simpler. Let's just think about graphs for now. So let's consider a bipartite graph X with sides X and Y. And the cylinder just means that we select a subset X prime of X and Y prime of Y, and we look at the Cartesian product X prime times Y prime. So that's a cylinder. And the cylinder partition is just a partition of X times Y into such sets. Okay, so far, nothing complicated. And here's the cylinder regularity lemma. So it was proved in the 90s by Duke, Lefman, and Rödel. And it says that we can always find the cylinder partition such that essentially most of the cylinders are epsilon regular. Now, we don't know that all the cylinders have the same size, so the right way to say most is to say that the weight of those which are bad is small. So the weight of a cylinder is just the product of X prime times Y prime. And we say that if we sum the weight of all of those bad ones, those that are not homogeneous, sorry, this should say regular, not regular, then this weight is at most an epsilon of a total weight. And the important thing, so far what I told you just follows from the regularity lemma. There is no news here. So the only news is that the number of parts is much smaller. Number of cylinders is only exponential in 1 over epsilon. So I want to show you what a cylinder partition looks like, because this is a bit confusing. So this on the left side is a normal partition. What do I mean? I mean I partition X, I partition Y, and then I take the Cartesian product of these partitions. That's a normal partition like in the regularity lemma. Cylinder partition is this weird thing where I'm allowed to partition into rectangles, but it doesn't have to come from a partition of X and a partition of Y. Okay, so here is again the cylinder regularity lemma. And now the question you can ask yourself, so why do we get this saving? What's happening here? So now I can tell you. The reason is, so suppose we have a partition already, and we have a certain cylinder, X prime, Y prime, which is not regular. Now, what does it mean that it's not regular? That I can find some piece here and some piece here that these two pieces behave differently than their parents. They have a different density. Now, if I only wanted cylinder partition, my life is easy. I just break this cylinder into 4 cylinders, right? This versus that, this versus that, this versus that, and this versus that. So the number of parts is only multiplied by 4. On the other hand, when I was proving the regularity lemma, when I do this for this, like for X prime versus Y prime, and then I do it with respect to some other set, I have here another part, and I want a normal partition, so I have to take the common refinement, the Venn diagram, and this makes the number of parts grow exponentially. So that's the reason why here for the cylinder regularity lemma, we only get an exponential dependence, and in the original regularity lemma, we get tower type dependence. Okay, so let me show you why this is useful. So let me prove the following. So if a bipartite graph has bounded VC dimension, then I can find the epsilon homogeneous partition into a double exponential number of parts. Now you can tell me why are you doing this, because you already showed us that there is a polynomial number of parts. And this is worse. But I'm doing it to illustrate how we use the cylinder regularity lemma, because then we also do it for hypergraphs, and this will be our proof. So somehow here, double exponential and polynomial is a big difference, but on the scale of like tower functions, we don't care about this exponential, another exponential, so it will not matter in the hypergraph case. Okay, so again, so this holds with polynomial dependence, but we're demonstrating this idea. So what we do, we take, let's say, epsilon to the 100 regular cylinder partition. The number of parts is only exponential. And we know that almost all the cylinders, so every regular one, has density which is very close to 0 or 1. So let's say at most epsilon square, or at least 1 minus epsilon square. This is because the VC dimension is bounded. Okay, so then what we can do, let's take the Venn diagram of the cylinder. So we don't want a cylinder partition. We're not happy with this. We want a normal partition. And it's not hard to get one. We just take the cylinder partition. So we look at all the sets which appear as cylinders here, and we just take their Venn diagram. So then the number of parts grows by another exponential. We're not worried about this. And I claim that still most of the pairs of parts have density which is close to 0 or 1. So instead of epsilon squared, this becomes epsilon. And this is essentially Markov's inequality. So if I have y prime and x prime, and let's say that the density between x prime and y prime is at most epsilon squared, so it's very sparse, then what happens when I take the Venn diagram is that I actually partition x prime to many, many parts, and y prime to many, many parts. But then because the density between x prime and y prime is very small, then I expect the density between most of these parts, pairs of parts, also to be small. Okay? And that's it, right? So that's the proof. So what we, okay, so here is an illustration of this. So this is the cylinder partition. It's a cylinder partition, and then we take the Venn diagram, which gives us this thing. So we just look at all the sets in X which participate in a cylinder, and we take their Venn diagram, and the same for Y. Okay, so here's this theorem again, saying that we can find a homogeneous pair partition where the number of parts is only a tower, and our strategy is the same. So what we do, we prove a cylinder regularity lemma for 3 uniform hypergraphs. So this is most of the work. And it turns out that, again, using a cylinder partition saves you in the dependence. So for graphs, it lets you go from tower to exponential. So this is one level down in the Ackermann hierarchy. And here it also allows you to go one level down in the Ackermann hierarchy. So from Wowser to tower. Okay, and that's the reason we get a tower type bound. So, okay, yeah, okay. I hope that was clear enough. Okay, thank you.